So today's topic is dual space to the Hilbert space. It is first part of our topic today, and second will be the convergence in the norm space. They're different, maybe. This in norm space. So it is two topics. So we start with this. On previous lectures we prove proved some theorems. For example, let 1 less or equal to p, p is less than infinity, omega mu measurable space. So omega is finite, sigma finite space, m is sigma algebra, mu is sigma additive measure. Then we prove that there is isometrical isomorphism between these two spaces. So L dual to LP is LQ, where 1 over P plus 1 over Q equal to 1. And I want to emphasize that if we attentively look on this theorem, then if P equals to 2, then Q equals to 2. So it is unique situation when parameters P and Q are the same. And there is a question: why it is? Is it a casual situation, or it is a special case for some special spaces? And we can see that for P equals to 2, space LP is Hilbert. So L2 is Hilbert. Hilbert space. So we prove that this is a situation when the dual space coincide with origin space is a typical for Hilbert spaces. So first I prove some lemmas. First lemma. Let X, Y are normed spaces. A is bounded operator. From X to Y. Then the kernel of A, which is by definition such X small from X capital, such that AX go to 0, which vanishes by operator, is closed linear subspace. Subspace in X. Let's prove it. The linearity is obvious fact, because operator A is linear and our spaces are linear. But we prove that first let x1, x2 belongs to the kernel of operator. Take this linear combination where alpha beta from C or from R complex or real numbers. Then by linearity of operator we can write it as following linear combination, and this by definition of the kernel are 0. This 0 and this 0, so the sum is 0. So we prove that it is linear subspace. And second, closed. So let's take the limit point. Let x0 is limit point for kernel. By definition of limit point in metric space, there exists sequence xn. What sequence? Each xn belongs to the kernel, and xn tends to x0 as n go to the infinity. But our operator is bounded, so A is continuous. And as it continues, then we immediately obtain that AXN tends to the AX0. But all these elements are 0 because xn are from the kernel. So by the limit we obtain from this, it follows that the limit can be only 0. So we obtain that the limit point belongs to the kernel. So kernel is closed. So we obtain that. So this statement is true for any bounded operator. For any bounded operator. Corollary, the functional, linear bounded functional is a particular case of operator. So corollary, let X norm space F small belongs to the dual space, so it is linear bounded functional. Then the kernel of F is closed linear subspace in X. So the second question which we need to discuss, what is the dimension of kernel? Of course, the most interest for us is the infinite dimensional spaces, because in finite dimensional spaces the description of dual space can be obtained from the facts of linear algebra. So more interest situation, I repeat, when the X is infinite dimensional space. So just now we consider only a Hilbert situation, but fact is valid with certain changes in arbitrary Banach spaces. But lemma 2 I formulate and prove only for Hilbert space. So let H is Hilbert. Define H0 just a kernel of F where F belongs to the dual space. So it is bounded linear functions. Then the dimensional of orthogonal complement to the kernel is 0 or 1. because it is integer number, so the orthogonal complement to the kernel is not large space. Some remark for Hilbert space, for Banach space. X is Banach. Space. F belongs to the space of linear and bounded functionals of a dual space. X0 let's define as kernel of this functional. Then the same statement. In Hilbert space we have operation of orthogonal complement. In Banach space we have no this operation, but we can take a factor space. It is a good space with factor normal because X0 is a closed space. So the factor space is Banach space 2, and then its dimension is less or equal to 1. So the kernel of functionals is large space. So, but I prove only Hilbert situation. So begin proof. It is easy. First, let we take a trivial functional, which is 0 almost everywhere. Then, of course, in this situation, the kernel of f equals to all space. So H0 is H, then H0 orthogonal is 0, and in this situation, dimension of orthogonal complement to the kernel, of course, equals to 0. This is trivial situation. And second situation, so there exists some element x which is not 0, x from Hilbert space, such that f of x is not 0. Yes? So there exist some non-zero elements on which of our functional gives us non-zero value. And let's further prove by contradiction. Let exist x1, x2 linear independent elements in orthogonal complement to the kernel. So we assume the dimension greater than 1. So we make an assumption that the dimensional orthogonal complement greater than 1. So with 2 or 3, or so at least we have 2 linear independent elements. And I remind you that the orthogonal complement, of course, is a linear and closed subspace too. So is linear and closed subspace. So any linear combination of 2 elements, x1 and x2, is from orthogonal complement 2. Let's consider element x, which I defined. So these elements both from orthogonal complement. So our functional on these elements is not 0. So let's consider the following linear combination. I remind that this is not 0 and this is not 0. Because are they from the orthogonal complement to the kernel. They are not in the kernel. But, so it is linear combination, so it must lie here, because it is linear subspace. But if we take our functional f and calculate the value of functional on this element x, it's easy to see that it is 0. It's easy to see that it is 0. So we obtain that x lies in the kernel. In the kernel. Combining these two facts, we immediately obtain that x is 0. So we obtain that this linear combination is 0 where these coefficients are not 0. So it is contradiction to the linear independence. It's contradiction for linear independence of x1 and x2. So let's finish our proof. And we're ready to formulate and prove our main theorem, so-called Riesz theorem. Let H be Hilbert space. Then the dual space is isometrically, we have an isometric isomorphism of dual space, but it is linear conjugate. So I write in brackets linear gate isometric isomorphism. In situation of complex linear conjugate, in situation of complex spaces. So I just explain what means this all words. So for any f belongs to H star from dual space, there exists unique y from H. So we have one-to-one correspondence. One-to-one correspondence between elements from dual space with elements from our Hilbert space, such that for any x from H, f of x can be written as scalar product. So any functional in Hilbert space, it is a scalar product with fixed element. We have one-to-one correspondence between functionals and elements in H. What does mean isometric? Isometric means that the norm of functional, as we calculate by definition as supremum of action of functionals on unit ball, coincide with the norm of element y in H. This means isomorphism, or isometric. But if we have two functional, if I take another functional g from H star, we have one-to-one correspondence with such element z from H, and for linear combination of functionals, we have correspondence y and z. Y and z. So it is, if you see, in complex space, H over C. Of course, if we consider real spaces, it is usual isomorphism without any conjugation. But in complex space, we have linear conjugation isomorphism. And it is, we have no contradiction between previous theorem when we prove for L2 small or L2 capital, because in these theorems we describe the functionals not as scalar product, as sum. So it is no contradiction with previous results. For example, some remarks between proof. In L2 small, for simplicity, in L2 small, we prove that for any functionals from L2 star, there exist unique y from L2 2 and f of x as xi, yi, the sum of I on infinity. And this is usual isomorphism. So linear combinations go to the linear combinations, but it is not a scalar product. Scalar product in complex spaces must be written in following. We have a conjugation of a second argument in the scalar product. That is the difference between different approaches to the functionals. Or you describe the functionals as a scalar product, but we must work with the linear conjugation. Or you can describe usual isomorphism, but it is not scalar product. But for many situations, it's more convenient to work with functionals as scalar product. As a scalar product. Maybe I then consider some examples. So prove the theorem. The proof of the theorem. So define H0 as kernel of our functional f. And by lemma we know that the orthogonal complement, the dimension of orthogonal complement is 0 or 1. So first situation, if f is trivial functionals, is identity 0, then we obtain that the H0 coincides with H, then take y equals to 0. Of course, it is the unique correspondence to f, because only for 0 element the scalar product is 0. So we obtain the description of our functional as a scalar product with 0 element. Of course, it is in this situation, it is unique. Second situation, f is not identical 0. So we know that orthogonal complement is 1. So this define H1 as orthogonal complement for H0, and according to theorem of orthogonal complement, we can obtain the decomposition of our space H. So then H can be represented as direct orthogonal sum of H0 and plus H1, direct sum. Of course, any element, for any element x, we obtain its decomposition as sum of corresponding elements, x0 from H0, x1 from H1. And of course, our functional on x0 equals to 0 because it is from the kernel, so it is sufficient to describe how it works on x1. So we obtain that f of x, but x1, what we know again about space H1? H1 is one-dimensional space. It has a basis. Let the basis in H1, or H1 is a span, linear span of this element. Of course, it is a non-zero element. Then any element x can be represented in the following manner. With some element x0 from h0, which doesn't matter because, it's not functional, it is element. But f of x is equal to this. So we obtain the result of our functional on arbitrary element x. And again, idea, let's try to find y idea. Let's try to find y from h1 only, from only h1. And then we prove that it is unique, so idea will be correct. We show that by this way, this idea is correct. But first idea, let's try to find y for our scalar product from subspace H1. So if we try to find y from here, then y looks like beta on the basis element. And now calculate scalar product. Plus alpha E1, it is x with y. So x0 from h0, y beta E1, and this element is orthogonal to E1. So by definition of our scalar product, we immediately obtain that it is alpha beta conjugation with norm. Of course, I can take a normalized basis element, but it doesn't matter. Without normalization, we obtain this number. And what we want? We want that this number coincides with this number. So for any alpha, for any complex number alpha, because it is just a representation of element x arbitrary. So we immediately obtain the formula for beta. Beta equals f E1 divided on the norm of E1 power to 2. So we obtain this element y. So our element y. So if y looks like f E1 divided on E1 square E1, then we immediately obtain that our functional coincides with the scalar product. We especially choose parameter beta. Choose parameter beta. Why? But of course, we we consider y's elements y's only from subspace H1. The question, may be possible to construct our functional with another element z, which belongs to not only to H1, but belongs to the sum, have non-zero component. So if uniqueness, if exists z which is not coincide with y, such that fx looks like scalar product fz for any x, subtract these formulas, and we immediately obtain that 0 equals, by linearity of scalar products, for this. So this scalar product is 0 for any x. For any x from H. So this element y minus z orthogonal to whole subspace, so it is possible only if y coincide with the z. So this representation is unique. And what we left to prove? The isometry. So only unique fact is the isometry. By Cauchy inequality, Cauchy-Bonikovsky or Cauchy-Schwarz inequality, we know that this inequality true. From this inequality, we obtain that the norm of functional less or equal to y. But if we take x, for example, with this normalization, we have the norm of x equals to 1, and f of x just equal to y. That's all. So with these two facts, we immediately obtain that the norm of functional as supremum of all on unit ball, it is from the unit ball, coincides with the element from H. From H. That's all. So with this finish our proof. And now some examples which allows us make some calculation more easy. The first example is very easy. So let's L2 0 1 and functional f capital on f small function equals integral from dx. So what is the norm of this function? We see that this scalar product with yes, it is easy to see that it is a scalar product with the element g. So the norm of functional f equals to norm of function g, which is equals x dx and square root, so it is 1 square of 2. So that's all. That's all. So the theorem says for us that any function is a scalar product, and in this situation it is very easy to see with which function it is indeed scalar product. It is very easy situation. More difficult situation I consider a few minutes later, but just now I want to give an additional notion. I want to define so-called what it means, this abbreviation, reproducing kernel Hilbert space. It is very important notion as for geometry of Hilbert space, for general theory of Hilbert space, but it is very important, for example, for the mathematical physics, because reproducing kernel I just define what is reproducing kernel and what is the reproducing property. For example, for differential equations, because reproducing kernel is a green function for differential equations, so it gives us a solution. That's in short. But definition. H is a reproducing kernel Hilbert space if first H is a space of functions on some set omega. First, space of functions, it's not just the functions. And second, for any number, for any point from omega, the functional, the value functional at f from h, and for any f from h, the functional which gives us a value of function f at point A, a value functional so-called, is linear and continuous functional. So by this theorem, what we know? So this functional belongs to. So let's define it as this functional as f sub a f. Yeah. So this which gives us a value. This is functional f a capital belongs to the H star, to the dual space, because it is a linear continuous function. So by this theorem, there exists element GA in H such that FA of F can be written as a scalar product. As a scalar product. And then what we can do following. Let's take another point. Another point. And FBF point belongs to omega. FBF is a variation functional at point B. At point B. So again, by this theorem, there exists function GB from H such that f of B is the scalar product with this function GB. And then, but I remind that this is a parameter. A scalar product we take on another variable. So this is in this situation or in this situation here parameter A is fixed parameter for fixed point. But then we can consider following function of two variables. I take two functions, one with parameter A, another with parameter B, and then we can allow to this parameter changing all set omega. So we obtain a function of two variables on omega square. And its complex function is omega to C. I consider in the usual situation the complex Hilbert spaces. This function is a reproducing kernel. This function is reproducing kernel. What it reproduces? It reproduces a value of function f. Moreover, it is easy to see, by reproducing property of function g sub a, it equals the value of function g sub b at point a. Or it equals, in complex situation, it equals a conjugate value of function g sub a at point b. But if you consider, for example, real spaces, of course, this is a symmetric function. It is a symmetric function in a real valued situation. So let's consider some examples. Again, some examples. So the main importance and convenience of reproducing kernel Hilbert space is this simple property. Examples. First example, L2, for example, on AB with standard Lebesgue measure, is not a Hilbert space with reproducing kernel. Why? Because, look please at first assumption. A Hilbert space must consist from functions, but L2 on the interval, L2 on the interval is a space of class of equivalence. It is space of equivalent classes. So the element of L2 on the interval is not a functions. It is a class of equivalence. The element that is all class of equivalent functions. So for functions from L2, the notion of value at point is incorrect notion. It is not well defined in this space, because you can change your element from L2 on any set of measure 0. So you can change it at one point, so we don't know what is the value. So it is not a correct defined function. So it is not Hilbert space with reproducing kernel. Second, let's consider, for example, Rn. And it is a Hilbert space with reproducing kernel. Why? What is the element of this element? It is a finite dimensional vector, with scalar product of finite sum. What is the value at point? The value at point, our omega is just the first, and if we take function, so it is a xk. Xk just a scalar product with element A with the basis element ek. Where unit is on the kth place and other coefficients are 0. So we have a function which gives us a value for element x. It is a function on this set. This is vector is a function of this set, and the value at point is this scalar product with such element. So you immediately obtain that the So it is reproducing kernel is a identity matrix. And a more general class is for reproducing kernel Hilbert spaces is Sobolev spaces. Because Sobolev spaces is spaces with where we can define in well way the value at 0. So let's third example. Let's consider for simplicity 1, 2, minus 1, or maybe 0, 1. For symmetric, I take this. And let's take a scalar product in this space. Let's consider real over R, real spaces. And what is this space? So this space is function which absolute continuous. So it is good function, absolutely continuous. So the value at point is well defined, and this derivative f prime belongs to L2. And we make this space with Hilbert structure, with the Euclidean structure, with this scalar product. And let's take any point A from minus 1, 1, and consider functional which gives us a value at point A. So we show that it is indeed continuous functional, and by Riesz theorem it can be represented as scalar product with and questions. First GA, second reproducing kernel KB. What it means. So let's try to calculate it. So we know that our functional f of a by Riesz theorem is a scalar product. And idea what we can do with the integrals to obtain the values at points. The simple idea to make integrations by parts for second integral. So second integral, let's divide it on two parts. I just work only with this. dx. And let's integrate by parts all these integrals, putting the second derivative on function g. Yes, there can be problems because our function g is from space W1 so it have only one derivative. And if we integrate by parts, we obtain second derivative on function GA. But let's hope that we succeed in this way. So what we can do? This is f g a minus 1 minus integral a f g double prime dx plus f, sorry, here 1 dash f g a from a to 1 minus 1 sorry a 1 f g And here, this integral we can write as sum of two integrals and combine with these integrals. So we have no integral parts in the left side. In the left side, we have only the value at one point. So we have no integral. These two integrals must vanish with these two integrals. So we obtain two different, more precisely, one differential equation on function g, but on two different intervals. We have this differential equation on minus AA, and for the same equation on A1. But we need to solve it apart. Not on the whole interval, but apart, because we have some discontinuity. The derivative of function g is not continuous. It is from L2. It is from L2 by definition of our space. So if we write this, so this reduced with this integral and this reduced with this integral. So we have no integration paths. And now let's calculate what we obtain by other elements of our integration by path. Fa g prime a minus 0 from the left, minus f minus 1 g prime I minus 1. And from here we obtain plus f1 g prime 1a minus f a g a prime is a plus 0, because it's left limit to the right. So we must vanish these terms for any f. For any f, so we immediately obtain that for this g prime a minus 1 must be 0 and g prime a at 1 must be 0. And if you combine these, we immediately obtain that we have this term minus ga a plus 0. So if you combine this left side and what we leave at the right side, you see that we have a jump for the derivative at point A. So g prime a minus 0 minus g prime a plus 0 must be 1. Must be 1. And additional assumption, our function must be from Sobolev space. It must be absolutely continuous. So we must add this condition. This condition. So let's try to find the solution. So I take away these auxiliary calculations. We obtain these conditions for function g. If we find it from this space, from W, then by Riesz theorem we find the representation of our function. We can see that we have a differential equation of the second order. The basis solutions are exponents. But if we see on the boundary conditions, it is more convenient to try to find the solution not in exponents, but in another linear combination of exponents, hyperbolic functions. Hyperbolic functions. So if you see, we know that the hyperbolic sign at 0 equals to 0. So let's try to find some constant on this interval. if we take a derivative hyperbolic cosine change to the hyperbolic sine, and at point minus hyperbolic sine with this changing of variables, of the shift variables, will be 0. And the same we do on additional interval. So this is a solution on this equation. So these conditions are valid. And moreover, these conditions are valid. So we have two constants, A and B, and we have additional two conditions. So A this is a continuity condition. So we know what is constant. For example, B. And the cosine is not 0, so hyperbolic cosine is not 0. And the second, not second, but the condition on jump of derivatives. So from the left we have A. This is from the left minus A sorry, something wrong because there must be constant, yes, because I calculate the condition of continuity. So sorry, this is A plus 1 and here A minus 1. A minus 1. So B is a constant, it is not a function. A plus 1 and divided on A minus 1. Sorry, you must put A except x. So, and this is a derivative, this hyperbolic sine. Here is correct. So A plus 1, A minus 1, and the derivative on the right side is this must be equal. So it is equation on A. So let's multiplicate it on this cosine equals A plus 1, A minus 1, and if I remember correctly the hyperbolic trigonometry, it is just A plus 1 minus A minus 1 plus 1. So we obtain that A equals hyperbolic sine of 2, and B equals this is reduced, so we are ready to write our answer. Function GA of x equals on this interval and equal to on this interval. And now, for example, what is the norm of this function? So questions, the third questions is the norm of our function. The norm of our function. I start with the third questions. The norm of our functions is the norm of by Riesz theorem of element with which we take a scalar product. We can calculate, for example, the norm of functions GA from these formulas, but they are very difficult. But you can use reproducing property. By definition of the Euclidean norm, it is square root from the scalar product. And it is just by reproducing property, it is a value of function GA at point A. At point A. So it equals this value. Very easy. Very easy. What allows to us reproducing property. Of course, the more simple situation, when we take symmetric cases, A is 0, the center of this interval. So in this situation, equals to and then you can take again something property of hyperbolic trigonometry. So one cosine reduced, so it is half of hyperbolic cotangent at 1 for 0. So this we find, the answer here, this we find that reproducing kernel, but it is change what is, we consider over R, so it will be symmetric functions. So doesn't matter, it is GAB because we have real function, or GB of A, G sub B of A. So it is equals to what? If B less than A, and then we put B here, yes? We put B here, it is equal A minus 1 cosine B plus 1 over hyperbolic sine of 2. And if A, we can put B here. So it is so we obtain the answer for this at the reproducing kernel. So again, I repeat that Sobolev space and gives us numerous examples of functions of Hilbert space with reproducing kernel. We can change the smoothness parameter here. We can consider different boundary conditions, Dirichlet boundary condition, Neumann boundary conditions. So we can consider a lot of Sobolev spaces and a lot of reproducing kernel in these spaces. So just I finished first topic of our lecture on the reproducing kernel. And we consider second part of our lecture is convergences in norm space. Convergences in norm space. Different convergences in norm space. First situation, let X is norm space. Here we have standard convergence in norm. Xn converges to X in norm if the difference go to 0 in norm. But now we have weak convergence. I denote it as but it is more difficult notation, so it is more convenient this half arrow. So it is weak convergence, so we have not a full arrow, we have a half of arrow. By definition, it means that for any f from the dual space, we have a convergence of the numeric sequence. So just numbers. It's just a sequence of, we have a convergence of sequence of numbers because the values of functionals is a number. It is indeed more weaker convergence between as a norm. Let's prove the statement. From the convergence in norm, convergence in norm implies the weak convergence. Indeed, if we write by linearity of functional, we can write it as following, and then multiplicative inequality this is a finite number because we have a bounded functional, it is from dual space, and this go to 0. And example, where 2 is not go to 1. Let's consider H is Hilbert space. Hilbert space. And system. Of course, we consider infinite dimensional space. Then we can find countable orthonormal system. I state that this orthonormal system weakly go to 0. Why? We know that any functional, for any functional from dual space, we can write it by the Riesz theorem. By the Riesz theorem, we can write it as scalar product with some element y. But by the definition, it is Fourier coefficient yn, but it's conjugate. So remind our work with the Fourier coefficients. But Fourier coefficients, this is coefficient. It go to 0 as n go to infinity because Fourier coefficients belongs to L2 small. It's from Bessel inequality. From Bessel inequality, we obtain that the sequence of Fourier coefficients belong to L2, so it goes to the 0. But in first part of our statement, we show that if we have a norm convergence, then weak convergence is to the same element, But in norm, we have no convergence in norm to the 0 because the norm of any elements are 1. But we show that we have a weakly convergence to the 0. So if we have a non-convergence, it must be just to the same element to the 0. But it is impossible. Second part. Let X is norm space and X star is dual space. And now we can consider different convergences in the dual space. And in dual space, we have an additional convergence. Again, we consider the functionals. So Fn belongs to X star. First, we have again the norm convergence. as a standard normal space. It means that the norm of the difference go to this. Second, we have weak convergence. By definition, as a first step, by definition, it means for any f capital from the dual space to the dual space, so from the second dual space, f of fn small goes to the f capital of f small. But in dual space, we have an additional convergence. The third convergence is star weak convergence. It means that for any x from x small, fn x go to fx. It's point-wise convergence, just a point-wise convergence. It is to see that we have such implications. First, we prove in general situation, first implication. This implication, just I remind you the Hahn-Banach theorem and some corollaries from Hahn-Banach theorems. For example, we know that we have isometric inclusion, isometric embedding X to the second dual space. For any element X, we have correspondence to the functional from f capital sub X in this space, and this functional works as fx. So if we see the definition of star weak convergence, we see that this is such elements. So here we have all f, and here we have only from x. Of course, if x reflexive, then we have this isomorphism between our space X and the second dual. So these are all f. So in reflexive space, of course, weak convergence coincide with star weak convergence. So, and this is arguments show us that from weak convergence we have a star weak convergence. Again, I repeat that for weak convergence we must consider all f from X, and here we have only from X by this embedding. So not all, but a part of functionals. But in reflexive they are coincide, they are the same. And additional example from this. There are interesting examples. It's not easy examples, but it is possible to construct some infinite dimensional spaces where the norm convergence coincide with the weak convergence. And it is possible to construct not reflexive space, where weak convergence coincide with the star weak convergence. But it is not easy. Now we consider this example where 3 is not 2. We know that C0 star is isometric isomorphism with L1. And L1 is L infinity. So I consider L1 as X star, as a dual space. So let's consider weak and star weak convergence in L1. But L1 we consider as a dual space. We consider L1 as a dual space. Let's take Fn from L1, which is isometric isomorph to C0 star. And for F1, we one-to-one correspondence with such sequence from L1. And for any x from C0, Fnx equals xn is that a coordinate of this sequence, and by definition of space C0 it's go to 0. So we immediately obtain that this set of functionals goes to the 0 in a star weak convergence. But if I take functional f from L1 star, which is L infinity, which is defined with this sequence, this is from infinity, from the dual space to L1. So you can see that this f capital on Fn equals only 1. So here we have converging to 0, and this is not converging to 0, so Fn, we have no weak convergence. And the last part of this lecture is convergences. In space of bounded operators. Of course, we have a norm of operator, we have a norm convergences, but for operators it's more convenient to define another convergences because operator is described by its action on elements. So what we have definition? X, Y are Banach spaces. Space of bounded linear operators from X to Y. So AN, first convergence, AN belongs to this space. AN converges to operator A in norm is just the standard definition. Second, strong operator convergence is just a definition of, this is all words are part of definitions or part of the name of this convergence. Definition notation is strong, so we put word S, letter S from word strong. It means for any x from X, AN X go to AX in the norm of space Y. So it is pointwise convergence. So if you consider functional as a particular case of operator. So if you consider functional as operator, you can see that this is some mismatch of the definitions of the convergence. The star weak convergence for functional is a strong operator convergence. And third convergence, weak operator convergence. The definition is following the same half of arrow, and but definitions is following. For any x from X, from any y from Y star from the dual space, F, A, and X go to F, A, X. So for weak convergence for operators, we need to take the functionals from the dual space. But, Y. Of course, functional F. AX belongs to the space Y. So we can take functionals from the dual space to Y. And in Hilbert space, it is more easy. In Hilbert space, we know in Hilbert space, so A, N, and A belongs to the Hilbert space H, and A, N weakly converge to A if for any x, y from H, A, N, x, scalar product y goes to A, x, y. Because we know by Riesz theorem, which we proved today at the beginning of our lecture, all functional Hilbert space are the scalar product with some element y. So if we take arbitrary f, so we must take arbitrary y. It gives us arbitrary functionals, and here we must take arbitrary argument for the operator. And again, let's check that we have such implications and examples for that inverse implications are not valid in general situation. So let's show that from, first we show that from the norm convergence, we obtain the strong operator convergence. Indeed, it is easy. ANX minus AX. You can write it as AN minus A acting on X, and then by multiplicative inequality, and this go to the 0. So we obtain this. From second to the 3, the strong operator convergence implies weak operator convergence. So let's check f a n x minus a f x, and of course by multiplicative and by linearity of functional you can write this difference as following, and then use multiplicative inequality, and you obtain this estimation, and this term go to the 0. So we obtain that from strong operator convergence we obtain weak operator convergence. And about counterexamples. Let's consider L2 small, and I consider the family of projectors. The family of projectors on the first n coordinates. It's easy to see that this operator strongly converges to the identity operators. Because for any x, a n x minus identity x equals sum xk square, k from n plus 1 to infinity 1 over 2. And it is a tale of converging series, so it is go to the 0. But it's easy to check that this is they are not fundamental. So let's in the norm space. So they are not fundamental now. It's easy to check that they are not fundamental. Why? Because let n greater than m. K from m plus 1, the common part go away to n, here square, 1/2, it less than norm x. So it's easy to see that the norm of an minus am less or equal to 1. But if you here m, and if you take, for example, on this vector, but this is that it is 1. It is 1. So the norm of this difference equals to 1, not go to the 0, but we have strongly converging to the 0. And the last example, we show that from the weak operator converging in general situation, there are no strong operator converging. Again, in L2 small, let's consider the following operator. This operator is n power of right shift. It is n power of right shift. AR, X, shift, make a shift of the sequence. Put on the first place 0 and other elements of sequence of X go to the right. So I claim that this weakly converging to the 0 and strong operator converging. So let's check it, that AN go to the 0. Of course, because for any X and Y, let's write this scalar product. So I write here Y2, yn plus 1. So we see that this is xi n plus y, I from 1 to infinity. Take absolute value and use Cauchy-Bunyakovsky inequality. So you see that we have xa square I from 1. We have a norm of element x, but here we have from, as you see, place n plus 1. So this go to the 0 for any x and y, because it is a tail of converging series. So we have converging to the 0 operator in weak operator convergence. But of course, we have no strong operator convergence to the 0, because a n x equals to x. You see that this operator doesn't change the norm, so it is not go to the 0. So we have not weak operator convergence.